And here I share my screen. Okay. So yesterday, um, regarding during our discussion, I just learned that it is bit difficult for you to memorize the names of the chemical compounds like the multi-atom ions and as well as the this molecular geometry chart. So this is what I've decided. For any question that you have to have the knowledge on this, the chemical geometry, electronic geometry, molecular geometry chart information, that question will give you those information. That chart will be attached with that question. So I hope I'm gonna able to ease your work a little bit. So just focus on your uh, other materials then. Okay. Does it sound good?
Yes, thank you.
You're welcome. Right. Okay. Let's move to these questions. Right. So here, the in this table, we are given those structures, the molecular um, structures, the Lewis structures are given, and we are asked to determine or fill the table with the for this electron geometry, electronic geometry, molecular geometry, actual bond angle, polarity, and the hybridization. Right. When so this is regarding the central atom. Okay. So when you look at this, the central atom, we count in order to determine the electronic geometry, we simply count the number of electronic domains around this central atom. The electronic domains including the sigma bonds and the non-shared electron pairs. Right. When we count the number of electron domains around this A, we find four things: two lone pairs, two unshared lone pairs, and two sigma bonds. So there are four things around that. So the electronic geometry will be then the tetrahedral. Right. The molecular geometry, when we look at the molecular geometry for anything, if the central atom has any unshared electron pairs, then the molecular geometry would be different from the electronic geometry, because when the unshared electron pairs are present, they tend to stay as far as from each other. Therefore, these structures will deviate and will come to a different, a new new structure where they'll find the repulsion forces minimum, with the minimum repulsive forces. So in this case, these lone pairs would tend to stay as far as from each other. Then these, even the chart will tell you those information. So when we have two sigma bonds and two unshared lone pairs, the molecular geometry will be bent. Right. The actual bond angle. So the actual bond angle would be, if it is tetrahedral, it will be the typical, the bond angle will be 109.5, but this one would stay like this. If I draw it, A, So these are the lone pairs and here are the two Bs. So then this bond angle between these two Bs will be smaller than 109.5. Right. Because now, having these lone pairs, these bonds, the sigma bonds, have to be bit more closer than in the tetrahedral geometry. Look at the polarity. Yes, it will be polar because they are not staying completely opposite to each other. So we'll have a force over that side. So this molecule will be a polar molecule. Right. When now we look at the hybridization. When you need to count the hybridization, you count the number of sigma bonds and the lone pairs on the central atom. Right. So when we have four things, right, we have to altogether four things like two sigma bonds and two lone pairs. So so altogether we should have four hybridized orbitals. So four hybridized orbitals will be the sp3 hybridization. What are the four things? One s orbital and three p orbitals. So total would be four. So you'll count the lone pairs and the sigma bonds. And depending on that, you will decide the hybridization. Mm, any questions? Right. We'll move to the next one. Let me take another color. Good. Right. Now the central atom A in the next row has two unshared lone pairs and three sigma bonds. Right. So we have totally the electronic, how many electron domains? Five. Five things are there. So when five things are there, the shape, the geometry will be trigonal. Oh, what? Hmm, it is moves. Hmm, okay, this will be trigonal plane. Right. So the when we look at the molecular geometry, okay, now we treat the lone pairs differently from the sigma bonds. Like how this molecule actually being drawn, now they'll tend to stay as far from the each other. Therefore, the trigonal plane, and now we'll change to the T shape. Right. The actual bond angle would be less than 90 degrees. Hmm, I don't know why this found bit. Okay, let me figure it out why this is moving. Okay, so this will be less than 90 degrees. Right. The polarity will be this where the molecule, the bonds are not perfectly like they are not completely opposite. You'll see that. So there is a dipole moment. So the molecule will be polar. Right. The hybridization. Okay, let's count the things on the central atom. What are the things that we should count in order to determine the uh, hybridization? We count only the sigma bonds and the lone pairs. So there are five things. So in order to make five mixed orbital. So 5 mixed orbital. So sp3 and what's going on? Okay. So it will be sp3, but it has only 4 things, so we need to add one more. So the hybridization will be sp3d. Let me write it nicely. Hmm. Right, sp3d. So one is 3p orbitals and d. You will see there are 5 mixed orbitals. So that is how we determine the hybridization at the level of the GenChem 1. Right. Questions? Okay. We'll move to the next one. The next one looks bit easy than the previous two examples because the third one does not have any lone pairs on the central atom. So there are only 3 things. So when you have 3 things, it'll be trigonal planar. Right. So the when you just need to divide the 360 angle by 3, so this will be 120 degrees. Oh, the molecular geometry will be the same thing because there are no uh, lone pairs on it. So this will be the same thing here, but the bond angle would be 120 degrees. Right. The polarity. This will not be a polar molecule. The reason is when I draw something like this. Okay, so here we have the forces like this. So the total force would be over here when I uh, get the total from that. But that will be cancelled from the one on the other side. So we'll call these trigonal planar molecules as a non-polar molecule when the terminal atoms are equal. When all trigonal planar molecules are not nonpolar, when their terminal atoms are not equal. In this case, we have the same atom as the terminal atom. That's why this molecule has become a nonpolar molecule. Right. Now look at the hybridization. How many sigma bonds? It doesn't have any lone pairs, unshared lone pairs on it. It has only the 3 sigma bonds. 3 things, right? So it has only 3 things. So we need how many orbitals? Only 3 orbitals. How we can make that 3 orbitals? We start from the S and then adding a P. mm, And oh, what's going on? Okay. We have one S and P orbital. Oh, come on. I don't know. Okay. Right. Let me keep. Right. So this has one, uh, I'll make in the 3 orbitals. One is S. Oh, yeah. I know changing a color wouldn't help me with this difficulty, but let's see. Right. So this will be 3 things. So will be S, P, counting S and P makes 2. So I'll add sp2. One s orbital and two p orbitals make three things. So this will be sp2 hybridization. Questions? Right. Oh, next one. We have lots of lone pairs on this thing. How many pairs of lone pairs? One, two, three, four. And 4 plus 2 sigma bonds, altogether 6 things. So when it has 6 things, 6 electronic domains, we say it is octahedral. Right. So when it comes to the electronic geometry, all these lone pairs would stay as far from each other. Then the two sigma bonds will stay completely opposite to each other. You will see these lone pairs will, the way how they have arranged on around this, the central atom, they would be canceling out like that, repulsive forces. Then the molecular shape will be linear. Linear, right? So the bond angle will be 180 degrees, and this molecule, as it was the way how it was drawn there, you will see these the forces, the dipoles will be completely cancelling out. Therefore, this molecule will be a non-polar molecule, right? So now we have 6 things in order to determine the hybridization. We start with the S1. So we have 6 orbitals. So we add all p orbitals. sp3 counts 4 things. Then we have to go for the D. Then 5, we have to add a 2 more d orbitals, then it will make 6 orbitals. sp3d2 is the hybridization for an octahedral electronic geometry. Questions? Okay, right. We'll move to the next question. Right. So use the structure below to fill in the blanks. Number of sigma bonds. Right. Let's count the number of sigma bonds. One, two. In a pi bond, we when you see a double bond, a one bond must be a sigma bond. So it's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay, 13, right? Now, we have a triple bond here. In a triple bond, there is only one sigma bond. Therefore, altogether, we'll have 14 sigma bonds, right? How many pi bonds here? Okay, here is a one pi bond, and in a triple bond, there are two more, so 3 pi bonds. And here is a one more thing. So you can choose either one, okay? So there are 4 pi bonds as well, right? Next question. It is based on the table given, the structure shown above, right? Look at the carbon one. Oh, let me clear out the mess I have drawn. Right. Look at the carbon one. Here is the carbon one. Okay. What is the hybridization? In order to find the hybridization, we count only the sigma bonds and non-shared electron pairs. So carbon 1 doesn't have any non-shared electron pairs. We count only the sigma bonds. There are 3 sigma bonds. We need 3 orbitals. So the hybridization will be sp2. Right. So sp2 is a trigonal planar geometry. 3 things. Ideal bond angle. Ideal bond angle will be 120 degrees. but this that's why it said ideal. In actual molecule, this bond angle would be slightly different, right? So actual bond angle would be less than. So look at the hydrogen and hydrogen. When there is a pi bond, okay, so then these two hydrogen will tend to stay close to each other. Therefore, the bond between the bond angle between the hydrogen and hydrogen would be less than 120, but the bond angle between carbon and hydrogen will be slightly greater than the 120 degrees. Next, we'll move to the carbon 2. Again, let me clear that area. Right. So now we'll look at this, the carbon 2. Again, the carbon 2 looks the same way as the carbon 1. It has only 3 sigma bonds on it, so it will have the same hybridization, same ideal bond angle, and again, right, these the bond actual bond angles like the C3H. I do not expect you to give this the actual bond angles. I will not ask those actual bond angles for the exam. That's why I will just ask the ideal bond angle. So see carbon 3 and uh, hydrogen will be less than 120 degrees, and carbon 1, hydrogen and carbon 1 between carbon 3 will be greater than 120 degrees. I will, don't worry, this my writings on this document will look bit ugly or not clear enough to read. I'll make sure I'll post the answer key for this worksheet under the unit exam 2 review materials. All right. Next, we'll move to the carbon 3. Okay. Carbon 3 doesn't have any pi bonds. There are altogether 4 sigma bonds on it. So there we need 4 orbitals, 4 mixed orbitals. So this will be sp3 hybridization. Ideal bond angle will be 109.5, and the actual bond angle would be also, I would say, 109.5. Okay, again, you don't need to worry about these actual bond angles for the exam. Let's look at the N4. N4 is here, right? So it has 3 sigma bonds and 1 unshared electron pairs. So it has 3 sigma bonds and 1 unshared lone pair. So altogether 4 things. So it'll be sp3 again, 4 things. Bond angle will be 109.5, and the actual bond angle, I would say, less than the ideal bond angle. Right. Look at the carbon 5 here, over there. Right. It has 3 sigma bonds, because in a double bond there is only one sigma bond, the other one is a pi bond. So there are only 3 things. So the hybridization will be sp2. Ideal bond angle should be 120, since there are only 3 things on the central atom. And again, the between carbon 3 and carbon 5, I would say carbon 3 and carbon 7. Carbon 3 and carbon 7 should be less than 120 degrees, but between carbon 5 and oxygen should be greater than 120 degrees. Right. Let's look at the oxygen. Right. There are 2 lone pairs and 1 sigma bonds, altogether 3 things. So the hybridization should be sp2, since we have 2 things. You don't need to worry about the ideal bond angle, since this is bit different for the oxygen, right? Yeah, okay. Carbon 7 over here. Let me clean that out here. The carbon 7. Now the carbon 7 has one sigma bond and one triple bond. From the triple bond, we take only one sigma bond since other two are pi bonds. So there are only two things on that carbon 7 that we should consider for the hybridization. Two things are satisfied with the sp hybridization. We need two orbitals. One s and p brings that the requirement. All right. Ideal bond angle. So there are only two things. So that will stay as far from each other, completely opposite to each other. So the ideal bond angle would be 180. So there are no lone pairs on it. So I would think the pi bonds would stay, wouldn't do the wouldn't bring anything like it is. You'll see that around in the carbon 7 and carbon 8 it is not that crowded, so actual bond angle would be also 180 degrees. The carbon 8 looks the same. Carbon 8 has two sigma bonds, only two sigma bonds, because it has a one single bond and the other side we have a triple bond. So it has only two sigma bonds, again two things. So that is required by that requirement is fulfilled with the sp hybridization. Bond angles would be 180 degrees in both cases. Questions? Right. I will move to the next one. Now, we're going to calculate the bond orders, right? Bonding order. What is the equation for the bonding order? Bonding order will be equal to the electrons in the bonding orbitals minus electrons in non-bonding or the anti-bonding orbitals divided by 2. That is the equation that you must use to find the bonding order. Right. When we look at the bonding order, right, what is the when you see these stars here, the when you see a star here, uh, when you see a star here, that means it is an anti-bonding orbital. Or the electrons filled into those anti-bonding orbital will destroy the bonding properties of the molecule. That's why we subtract the electrons from the bonding orbitals that are filled in this anti-bonding or non-bonding. So electrons filled in the bonding orbital. This is a bonding one and this is a bonding one, and this is also a bonding one, but it doesn't, that orbital doesn't have any electrons in there. So let's count the electrons in these bonding orbitals. 1, 2, 3, 4. So 4 minus, right, what are the how many electrons do we find in the anti-bonding orbitals? This is an anti-bonding orbital, and here is anti-bonding, also an anti-bonding. So there are two electrons in anti-bonding orbital. So we divide that by 2. So you will get the answer as 1. Right. Next one. Let's move to the next example. This is a bonding. This is a bonding. And this is a bonding. So altogether, how many electrons are in bonding orbitals? 1, 2, 3, 4, 5, 6. 6 minus, right. So how many electrons in anti-bonding orbitals? This is an anti-bonding orbital. Here is an anti-bonding orbital, right. So 1, 2. Oh, there are only two electrons are filled into these anti-bonding orbitals. So we divided by 2 and the answer will be 2. The bonding order will be 2. That means it is bond, the molecule has a double bond between those two atoms. Right. The next one, next example, right. Here again, this is a bonding orbital and a bonding orbital, right? One, two, three, four, five, six. Six electrons are in bonding orbital and antibonding two, right? So divided by two, so the answer will be two. When we go to the next example, this is a bonding orbital, and here is a bonding orbital, and here is a bonding orbital. So let's count the total electrons in this bonding orbital. One, two, three, four, five. So there are five electrons in bonding orbitals minus the electrons in antibonding orbitals. Antibonding 2, and these antibonding orbitals are empty. So 5 minus 2 divided by 2, that will be 3 over 2, or it will be correct if you mention it as 1.5 as well. Right. Okay, so that's all for this, the worksheet number 3 for the unit exam 2. Okay, do you have any questions?
Um, no.
Okay, right. So I will stop sharing the screen. And again, thank you so much for joining with me. And please email me if you have any questions. Again, that the document, the chart for the electronic geometry and the molecular geometry will be attached with those questions. Okay, so you'll be given the blank paper for the scratch work, so you can copy it down to your paper, and you can use it for the other questions. Right. Okay, then I hope you all will do great on the unit exam too, and have a great weekend.
You too. Thank you.
Thank you. You too.
You're welcome. Bye.